Um, Hello, everyone. My name is Pedro Barret. I'm an architect at Crosslake, and I've been working with Mojaloop on and off for almost 2 years now, mostly focusing on the performance and scalability aspects of the open source. So earlier this year, we started this PoC initiative, which is about anticipating the next level of scalability and performance. It's also about bringing down the cost for the initial deployment and understanding how much each scaling step represents in terms of cost. This exercise was focused on the central ledger components as they have the biggest impact on the switch's ability to process transfers quickly and at scale. So we'll quickly go through a few slides just to recap the context. So from the start, we established two milestones to which we added a third one. The first milestone was to test the scalability of the new central ledger design according to the guiding principles, which were a pure event-driven and microservice design that had no shared data, where all central ledger components own and hide their own data. And we communicated exclusively by events without any database-controlled transactions. The second milestone was to investigate other principles like CQRS and event sourcing. These two in conjunction would allow us to send messages to Kafka that signal both a complete task and carry the state that will trigger the creation of a set of projections or views for the other part of the system to create the read aspect of it, the read side of it. These patterns are obviously not new and are used extensively in distributed systems such as Amazon or LinkedIn. And they have obvious advantages in terms of scalability and performance, but they come with added complexity. The objective of the second milestone was to prototype them and understand where and how they could be a benefit for us in the central ledger. We have achieved the first milestone last PI, the second one a couple of months ago at mid-PI 11. And last week, we released the first draft version of the report out document with all the details of how the PoC is built, including the list of things that need attention to make it production ready. So to recap what that all means, the focus is the central ledger. So we started by splitting the transfers and the participants into dedicated services so that they could do their own things really well. And then designed the whole transaction as a series of messages being passed between those dedicated services. We then proceeded to building that more granular event-driven transaction flow, applying single responsibility microservices for the participants and the transfers, which are clueless about each other, and they only communicate through events. Obviously, we tested this to see if the system was still scaling and performing well before proceeding. It actually did. So finally, we built the event sourcing mechanisms and the CQRS read projections. Again, load testing all of these mechanisms to make sure everything still scaled and performed adequately. So we have now achieved all of the objectives that we've aimed for. We have an event-driven event sourcing and CQRS design working and tested. We have achieved the 5,000 financial transactions per second. We, as mentioned, we have released the draft version of the report out document, which is in the first round of reviews. So we now have to spend some time making this code production ready. This will obviously require a lot of work. In this PoC, we have designed the flow without failure modes besides the happy path. We know we need to build those things now. We need to do more testing. We need to do better monitoring. Essentially, we need to make it production ready. This is the component diagram of the participant side of things. This is really big. It serves a point. In red, we can see the command side components, and in blue, the query side components as per the CQRS separation pattern. The thick boxes that you see, they're actually the services, the ones that actually get deployed. So these are the services that will then be deployed as a Kubernetes component. The diagram serves mostly to show the way the PoC is designed in regards to code and component organization. We have followed the domain-driven design tactical concepts. especially around the dependency management and the abstraction of infrastructure components. This effort will pay off in the long run with increased extensibility and maintainability. The big objective is that we have a layer of decoupling and abstraction between the valuable code that we have that takes care of processing transfers, the state of the transfers, exactly how the system does what it needs to do from the business logic perspective, separating those things from the less valuable aspects, which are the details about the infrastructure. So are we using a certain technology for the database? Are we using a certain technology to pass the messages? This design that we have abstracts those aspects of the infrastructure, having decoupled all of them from the valuable code that actually takes care of the business logic. So this is an important diagram, not to show that we're able to do very complex things, but to show that we took a lot of care in separating the code components so that the system could not only scale, but also be extensible in the future. We know that systems need more functionality as time goes by, and this is an important aspect. So this is exactly the same component diagram, but for the transfer side of things. You'll notice that is less complex. That's because we're not doing event sourcing for the transfers, as it didn't add any value, and it was just adding unnecessary complexity. We'll go through the details of this now. Later, Miguel will explain how it works with some detail. So this is what it means. This is the sequence diagram with a split between the transfers and the participants. This is what we call a saga choreographed strategy, where no part of the system knows about the whole, and the parts only know how to react to events and do their own task. This is opposed to the typical orchestration strategy, where there's at least one component that knows about the whole thing, and knows the whole state about the application, and is the one calling the shots and telling the different parts what to do. So this is a different way of designing systems. To stress it again, we designed the system so that the small parts only know what they need to do when they receive a certain message, and they know that when that message comes, they need to do a certain task. This obviously has the effect of making all of the components really simpler. So they are focused, they know exactly what they need to do, they have no idea about what happens on the outside, which leads to smaller components. So it's counterintuitive at first, but it actually leads to less code and less complex code in each of the individual parts. There's an aspect to this as well, which is about how easy it is for a developer to start adding functionality or to fix something. Instead of having one bigger system or lots or less parts that are more complex, we now have many parts that are smaller in functionality. So on one side, the system is more complex because there's more parts that talk to each other. On the other side, every time that you go to a certain code base, that code base is doing very focused tasks, very focused, oriented on only what they need to do, what they need to know, which in turn makes the code easier to understand and easier to contribute for other developers. So the flow that you're seeing is only the happy path. We actually designed and accounted for the known failure modes just to see if we were not designing something that would not be feasible and not be real. We just didn't build it. We didn't have time. This is a POC. That's obviously going to be part of the effort of making it production ready. So we can see that we have new services for participants in green and the transfers in yellow. The ML API adapter and the notification services are still the same, with minor changes to accommodate the different topics and the new end-of-life messages sent from the central ledger. One thing that you will immediately see is that a single transfer is now broken up into about 13 messages that flow across the central ledger services. This sounds like a lot of back and forth, and it's going to take forever to complete a single transaction. It's actually performing better than the current design. So Miguel's going to now explain how this all works in detail. Go for it.
Hey everyone, my name is Miguel de Barros from Motorsbox, principal architect working on the open source funded development project. You've probably seen me talk a couple of times over the last couple of days. Thank you, Pedro. So, so this is deployment architecture. Everything you see here is a deployable artifact. There is a Helm script that deploys all this with configuration, etc. So if you go to the PoC GitHub repository, all this is available. The only caveat on the far right, you'll see that there's 2 query handlers that have not been done. But regardless of that, on the far left, we have the ML API. You can see it's split into the service and the notification handlers. And then we have 2 distinct boxes here, which are pretty much matching or parallel of what you saw in the previous architecture overviews, where you can see the command side and the query side. And in the command side, you can see the distinct separation between the transfers and the participants. You can see that there's a domain event handler for each of them, and you can see there's a transfer command handler for each of them. And you can see the interaction between the Kafka topics and how they flow through the system. Also take note of the command handlers in terms of how they produce messages to which topic. So for example, the transfer command handler produces to a state event topic and a domain event topic, and the participant command handler produces to an additional snapshot events topic. And that's purely because the participant command handler uses a mechanism or a pattern that is called event sourcing, where the transfer command handler does not. I'll talk a bit about that a little bit later in terms of lessons learned. Also take note the data stores. So for example, the transfer command handler interfaces to 2 data stores, a duplicate store and a transfer store. And the participant handler interfaces to participant store, sorry. And this is a great outcome in terms of the architecture. It allows us to have a good separation of concerns, even from a data perspective. So in fact, on the transfer side, we separate the data based on also the workload type. So for example, the transfer store is more of a cache mechanism, where the duplicate store is a persistence mechanism. So that's one of the great benefits of this kind of architecture. It really gives us that separation of concerns and a way to control in terms of how we manage our data and how we wish to basically optimize that. On the far right, you'll see that we have the query side. We currently have 2 event handlers, one for participants, one for transfers, and they currently synchronize the data from the state events and the participant events and the snapshot events on the participant side as well into a materialized query store, which at the moment we're using MongoDB. It's worth mentioning that this was done for the PoC purposes, but if we were to fully either productionize this and integrate this into the current stack, we would easily be able to swap out, or not necessarily swap out, but we could create new state event handlers and synchronize to the existing central ledger database in parallel to this as well. And at the bottom, you can see we just have a metrics exporter. So that's basically a component that listens to the domain events, and that publishes the end-to-end financial transaction metrics to the Prometheus cluster that we have for monitoring the performance metrics. And you'll see a little bit later some screenshots of what that looks like. And it's also worth mentioning that every component here is pretty much a microservice, and the data stores are all distributed. So everything is scalable depending on how you wish to deploy and configure this PoC. Pedro, next slide, please. So let's talk about performance. So this slide's a bit busy. There's quite a bit of stuff, so I'm going to focus on the important bits. On the top left there, the top table is pretty much probably the most important table here. We have 3 rows. Each of them are an indicator in terms of the target performance figures that we wanted to meet. So for example, the first row is the financial transactions per second. And this is the financial transaction from an end-to-end perspective. It includes both the prepare and the fulfill legs. The second row is the time for the runs. Our target was 1 hour, but we always ran 1 hour, 20 minutes consistently, just to make sure there's a bit of headroom and to make sure there's no weird things happening. And the third row is basically the percentage of transactions that took longer than a second. And our target was to ensure that we had less than 1% of the transfers that took longer than 1 second. And then you'll see a couple of columns. The first column is the cost scale units. So this is included just for completeness. And this is actually the performance figures for a minimum hardware deployment to achieve 1,000 financial transactions per second. Let's put it this way. I will talk a little bit more about that a bit later, but inevitably the more interesting bit here is the next three columns, the 8 FSBs, 16 and 32 FSBs. It's important to note that we can't compare these directly to the cost scale units because the cost scale units were completely self-hosted, where the eCache, we used a managed elastic cache, which was a replacement for Redis. And the reason we did that is initially we were using a single Redis server for each of the data stores you saw previously, and we were hitting IO limitations from a networking and IOPS perspective. So we switched to this managed Redis caching solution, which was clustered and partitioned, and basically we used that to run our benchmarking figures here. And you can see the diagram on the right is represented in terms of what are the figures we got from a financial transactions per second. The green line is what we achieved. So with 8 we hit 1,600. With 16 we hit 3,000 financial transactions per second, and for 32 we just hit above 5,000. But you'll also notice a blue line, and that represents the theoretical limit, and that is based on a calculation from the slowest component within the system. So I'll talk a bit more about that a little bit later when we start talking about scalability. But in theory, we should be able to achieve that blue line. And as you can see, we're kind of close there at 1,600. We're pretty much spot on with 8 FSBs. At 16 FSBs, we're just missing it. And at 32 FSBs, we're a bit lower down. But relatively speaking, we are very close. We're not that far away. The bottom left table, the most important thing is just kind of indicating the let's say latencies, the response times you can expect from an end to end. So for example, with the 8 FSBs, it was 63 milliseconds, the average, and for 32 FSBs, it was 43 milliseconds. And we also have the minimum and the maximum. And at the bottom, we have the total transactions that were done during that 1 hour and 20 minutes. I think we can go to the next slide. And this is just to show that we could even do better once we figured how to actually deploy our own self-hosted clustered Redis environment, which was fully sharded. We were able to achieve even better figures, and we were able to even get closer to the theoretical limit in terms of the 32 FSBs here. So the top left table is pretty much what the same indicators you saw before. So we achieved 6,000 financial transactions per second, and our target was 5,000 for the time. It was 1 hour, or at least that's what's depicted here, but we still did 1 hour, 20 minutes. And the percentage of transactions that took longer than a second is just basically half of the 1% that we wanted to achieve, wanted to be below. So that is a great result. And on the far right, you can actually see those results shown from Prometheus, how we collected it. So we can see the processing time slots on the top part, just showing all the transactions and how they fit into the histogram data model that we use to collect the performance figures. The second part is the processing time for each of our components. So you can see that we know, sorry, not processing time, the processing operations per second, sorry, for the middle box. And there you can see the individual processing operations for each of our components, the participant handlers, the command handlers, the event handlers, etc., for transfers, etc. And you can see we even break that down per event type. So the 14 events you saw on the flow, you can actually see those here as well. But the most important part would be the end-to-end metrics, which is at the top. The merger TX transfers, that is the actual end-to-end financial transactions per second. But we even break that down into the separated legs in terms of prepare and fulfillment, which are the two metrics below that, which is TX transfer prepare and TX transfer fulfill. And the box below is just the processing time, which is just reflective of the minimum and the average and the maximum, etc., in terms of what the latencies are. And you can see there we're sitting at and a pretty good result there at 82 milliseconds on average at 6,000 financial transactions per second, which I think is a great result. And on the far left, we have a couple more boxes there, and that's just basically the hardware and infrastructure that we use to achieve these results. So the first box is literally showing you the core components, once again, the transfer event handler, the command handlers, the participant handlers, etc., and the ML API. The instance scale column, sorry, is showing you how many actual containers we used. So for example, on the first line, we have 80 transfer event handler containers that we ran for this. And on the right of that, we have the infrastructure type that we used. This is all on AWS. So we used C5 2x extra large. And on the next column, we have how many of those instances did we have running those workloads. So yeah, I think it's a great result. Yeah, team did an amazing job here. Do you want to go to the next slide, please? So from a scalability perspective, as I mentioned before, we had some limitations in terms of what we could do. And that theoretical limit, that diagram that you saw that we were trying to hit, is based on this calculation in terms of the slowest component in our system. And that component is the participant command handler. And because of the way that we architected the system using the CQRS pattern, the event-driven and these kind of patterns, and the way that we're using Kafka, we have a limitation in terms of how many of these participant handlers are able to process transfers at a time. Specifically, if we have however many X number of participants, we can only have X number of participant command handlers to maximize the processing of the position changes. So that means, depending on the kind of hardware you have, for example, based on the C5 2 extra larges that we used, we have a maximum of 400 operations per second per participant. And of course, a participant command handler is doing the prepares and the fulfills. So from a financial transaction perspective, we're actually hitting 200. And that table there is actually just showing the calculation, showing the cost scale units, that in theory, we can do 1,000 financial transactions at 5 participants, etc., all the way down to 192. And that's where we got that theoretical limit from. But you know what, we can actually do better than that. We can actually improve the performance. And there's a couple of points at the bottom of the slide just showing how we can do that. One of them is currently we're using a Kafka library. It does a lot of encoding and parsing, and it has some overheads because what it's doing is taking those message, there's some string manipulation, turning it into a JSON object, and that is quite expensive. And we can reduce that encoding by using things like protobufs. So if you use gRPC, you probably are aware of it, we can use that to optimize and remove a little bit of that middle man-in-the-middle string processing, and that would probably improve, or we believe it would improve the latencies with quite a bit of impact. The second thing, also the benefit of protobuf, it also gives you the ability to do some validations on the schema side, which we don't currently have at the moment. The second point is a separation of participant metadata, account, and endpoint information. So at the moment, we literally have a single object that we are storing in Redis that represents the whole participant. And that means every time there is a position change, we actually update the entire object. So we can optimize this by doing a bit of a separation of those different areas by moving metadata, account, and endpoint information into sub-objects. And we can do that in Redis by using hash sets, hash functions. And that would make life a lot easier, and it would optimize the overhead of just rather updating just those particular sub-objects of the main participant information. The third is virtual positions. And this one actually addresses the limitation that I described above with regard to how many participants we have versus how many command handlers we can have for the participants. So instead at the moment, as I said, we have 8 participants. That means we can only have 8 participant command handlers, at least from a processing perspective. What we can do is we can create this concept of a virtual position where each participant command handler pre-reserves a portion or a sub-portion of the position of that particular participant. And that means you can have many participant handlers processing position changes for the same participant, since they are managing sub-portions of it. Of course, this would potentially introduce a bit of complexity into the system, because now these participant handlers need to know how to reserve the position and create these virtual positions. And there's also a little bit of a challenge in terms of how do they address the situation when they run out of those, let's say, sharded positions. And there will need to be a bit of overhead in terms of how that happens. And there will need to be a bit of a process in terms of how they go and renew their positions as those occur. The fourth is about Bloom filters, specifically around our duplicate check of transfers. At the moment, we use a set data object within Redis to store every single transfer ID that is processed by the system. In theory, that is quite efficient, but over time of the hub's life, the actual size of that set might be quite big. And depending on, there's certainly, well, let's put it this way, there's certainly an argument in terms of how long we need to keep those transfer IDs, but in theory, if we're keeping them forever, it's going to be quite a lot of data. So we can optimize the way that we are storing that information by using a Bloom filter. This would introduce some overhead from a processing perspective, because the Bloom filters require some hash functions to occur to be able to create a statistical model for the duplicate checks. But at least from a storage perspective, it would be a massive improvement. It's still up for discussion in terms of whether this is even worth it or not, but it's worth pointing out that if Bloom filters were used, there is a possibility of having a false positive. It guarantees the false that there's never a false negative, but there is a case where there can be a false positive. And you can control mathematically and statistically what is the percentage or the probability of that happening, and that will have a bit of an impact in terms of the hashing functions that you use. But regardless, if that happens, we would have to have a backup in terms of also querying the long-term storage to make sure that if there was a duplicate found, we would need to just do an additional validation on the long-term storage side, most likely on the query side. The good thing is we don't expect many duplicates to occur, so this is really more of an outlier case, so it shouldn't really impact the performance of the system. The next is batching by FSPs, 0.5. So our underlying Kafka libraries that we're using to consume and process the messages through our durable messaging stream, a lot of it is managed automatically by some batching processing elements. However, from an application perspective, we are doing mostly things per transfer. So we're not really taking advantage of how that underlying library is able to batch a lot of the underlying messages and how they're consumed and how they're produced. So there is a bit of work and a bit of optimization that could be done to actually leverage on that batching capability by the underlying framework. This would improve the throughput of the system, but there would be an expense of an increase of latency. So it's worth mentioning that. So there definitely is a little bit of a, let's say, an exploration in terms of how much throughput we want versus how much latency we want, and how much batching will achieve that nice balance. The sixth item is about, well, we know that we hit the limit of 400 operations per second based on the C5 2 extra large. What happens if we go to a beefier, machine with a bigger CPU, a faster CPU? Maybe instead of having the 400 ops per second per participant, we're able to achieve 500 or 600 ops per second, or even better. So just by basically increasing the processing muscle, we are able to potentially improve the performance. And the last is Tiger Beetle. If you've been a participant on the previous MojaCons, you'll know that Coil had been very much busy developing Tiger Beetle. And what it is an optimized data store for handling and processing ledger entries based on an LMAX architecture. So once Tiger Beetle is ready for, let's say, for the spotlight, we could easily take that, implement it into the POC, replace Redis with that, and basically see what the performance is. There would probably be some changes potentially to the logic that we have in the POC, and maybe some slight architecture changes as well. I don't think that would be, I think that would be minimal though. And the reason for that is there's some of the actual ledger logic that we currently do in the application itself is moved down to the actual data store based on how it's processing the ledger entries. I think that's it. So what we achieved against our objectives, well, the first, we wanted to achieve a minimum deployment for 1,000 financial transactions per second based on those indicators that we previously discussed. So 99% of the transfers need to be below 1 second, and we need to be able to run those tests for 1 hour durability. And we've done that. We've established a minimum hardware footprint, what is needed for the POC, and we've called this the cost scale unit. And also importantly, this is on fully self-hosted environment. So whether you're on-prem or whether you're in cloud, you should be able to similarly create your own CSU benchmark and use what we have documented in this presentation, and more importantly in the report out document, which Pedro will talk about a bit later, as a guide in terms of what you can do to also achieve a similar result. Two, it's about the sublinear costs for scaling for each of these cost scale units. So basically, can you scale, increment, and how will the minimum deployment footprint match from an architecture perspective? And a lot of that has got to do with the isolation of how we've done the components. We're able to basically ensure that we're able to scale certain components in a certain way based on their characteristics. So for example, we can scale transfer components out much more than the participant components. And that's because there's a lot more transfers than there are participants. And a lot of the results of this you've seen based on this near scalability that we've shown above. The third point is just demonstrating the pure scaled performance, right? So we had the target of 5,000 financial transactions per second. And in theory, we will be able to achieve that with 5 cost scale units based on those minimum deployment and hardware footprints. What we've shown above and what we can show you based on the CSU is we've been able to achieve 6,000 financial transactions, which is 6 times the performance. So you'd expect us to be able to do that with 6 CSUs. We've, however, done it in 8. It's worth noting that we didn't fully optimize that footprint from a hardware perspective, and I'm pretty sure we could get that down to 7 from 8. So we're pretty much there, at least from a costing perspective and also from a scaling perspective. We're very much close to linear scale, I believe. And there's definitely more improvements that we can do. The fourth is basically understanding the characterization of the POC. How does the design scale? What was the maximum, the limitations of the actual POC? And we've shown that, and we've had a couple of discussions about that as well. There's a bit more information in the report out that I would suggest going through, but in essence, this is a moving target, right? Every time we basically come up with something, we're able to resolve it, and we're able to get higher or better results. It's worth noting that we're now at a point where we're not really optimizing code. We're not. Initially we spent a bit of time in the PI, the beginning of PI 11, doing that, but now we're actually spending most of our time optimizing the underlying infrastructure components, such as Kubernetes, the ingress or the gateway components for the API calls, and JMeter itself to actually run the tests at 5,000, 6,000 transactions per second. So we're pretty much at a point where we're starting to very much hit the limitations of our underlying environments. Can you go next slide, please? So learnings. So the first one is about limiting where we're using event sourcing. So the idea of event sourcing is we're writing the state events whenever we make changes to events to those state topics. And we're also creating a snapshot intermittently to basically have let's say a summary, a result of a time span in terms of what are all those results of those state changes. And we find that this works really well with participants, and that's where we've applied it to. But we also find that it didn't work so well with transfers. And the main reason of that being is that we have a lot more transfers than participants. And the mechanism of event sourcing is if the system goes down, it would be able to recover from that event stream and reconstruct the state in memory based on all those events. So since we have a few participants, that's relatively easy. And we are able to also snapshot those participants and basically crunch a lot of those individual state changes into those summary states. With transfers, that's not really possible, right? Because you have a lot of transfers and they're very much distinct little, let's say, transactions that occur, and you don't have any way of summarizing those in a nice way. So we found that it was very expensive to try and load that information from a topic and load that into memory. But on the other hand, participants is very well suited to that. Number two, which is about, let's say, caching on the command side for transfers. So number one, as I said, we couldn't use event sourcing, but on number two, on the transfer sides, we found that we were able to actually optimize the latencies of the processing by actually storing the transfers in memory caches. And this is possible because each transfer command handler that's processing and transfer will always process the same prepare and fulfill legs of that transfer. So that means we can store it in memory, and when the fulfill comes along, we're able to then load that in and then finalize that transfer itself. Of course, this does mean that from a backup perspective, we don't have the same mechanism that the participant side has with the event sourcing. So we rely on Redis for the, let's say, the resilient portion of that. So if for whatever reason we don't find the transfer in memory, we would go look in Redis. The third item is about compression. Initially, we started using gzip compression, and we did that for a couple of reasons. We wanted to reduce the overhead on a networking perspective by sending all these messages. As Pedro said, we have about 14 messages that are flying around per transfer. So it's quite network intensive. As such, we initially used gzip compression to try to reduce that as much as possible. However, we started seeing that we had diminishing returns when we hit around 4,000 financial transactions per second and upwards. We started seeing the actual overhead of the compression was becoming quite expensive. And as such, we actually had to switch it off to be able to achieve 4,000 and upwards results. It's also worth mentioning that since we're still, I've already mentioned that we were processing one message at a time when we were talking about the optimization with batching. If we did move to more of a batching model from a processing perspective, we would be able to optimize this because we wouldn't be compressing a single message at a time. Instead, we would be able to compress a batch of messages at a time. So there's a bit of more optimization that could be done then. The fourth is, I've already mentioned before, initially we started using a single Redis instance, and then we moved on to the Elastic Cache, the managed Redis sharded cluster on AWS. And so the final learning was basically us understanding that we need to have a distributed server for Redis. We already have one for Kafka, but we needed to be able to know how to deploy that and how to set up the sharding to overcome the limitations from a networking and an IOPS perspective. And in fact, initially, when we were deploying the single servers, we were deploying it based on the data stores you saw before in terms of the participants, the transfers, and the duplicates. With the Redis cluster, we were able to actually simplify it a bit more. We could actually then have two Redis clusters, each one optimized by workload, one specifically for caching and one for persistence. I think that's it for me. Thanks, Pedro. On to you.
Thanks, Miguel. We're really happy with these results. Not only we achieved this level of scalability, but we are sure we can get much more, as you've noticed from the amount of things that we have listed about how can we do this much better and more efficiently. And achieving this level of scalability and performance will really help our product and marketing positioning. We want Mojaloop to be competitive on scale, but also on cost, because The other side of scalability is that for those that don't need to handle this much load, the system ends up being much cheaper to run. And this is an important aspect. So one of the objectives of this initiative was precisely the cost aspect. We wanted to increase the resource efficiency and with that reduce the cost of entry and also the cost of scaling the system. If you recall the objectives, the minimum deploy unit was a system that could achieve 1,000 financial transactions per second with 99% of the requests served under 1 second during a 1 hour run. This slide shows the resources required for that minimum hardware deploy unit or cost scale unit, a CSU as we call it. And this is the configuration that is able to comfortably handle 1,000 financial transactions per second using 8 DFSPs. You'll notice that we have opted for more but smaller servers. And avoiding big machines was a conscious decision of ours. We wanted to ensure that we can deploy this in data centers where those big machines might not be available, or simply because some of those big machines are fairly new and recent, and there's a high cost to getting those machines. So what we tried was, let's try to have machines that would be fairly easy to obtain in data centers, or machines that are equivalent to 5-year-old machines that people have still lying around in data centers. Obviously, the tests that we run were mostly, not mostly, we're all using Amazon, but the way we have designed the system, which is exactly the same way as we have with the rest of the central ledger and the software, is based on Kubernetes, so it's all portable to cloud services, local deployment, even the infrastructure aspects, the infrastructure services that we have, such as Redis, Mongo, and Kafka, all of them can be locally deployed, and they don't have to be used on the cloud. Obviously, there's a benefit to using on the cloud when you can, because it's a managed service, and you eliminate that aspect of management. So this is the bottom number, 2,300 US dollars a month. This is the cost, the monthly cost for Amazon with just 1 year of reservation and no upfront payment. Obviously, this can be further reduced by paying more upfront or reserving for more than a year, for longer than a year. It's also important that you don't need all of this if you don't need to handle 1,000 financial transactions per second, so you can reduce it as mentioned. And again, this is the cost with the current system. We have plenty more tricks to unlock and to reduce to increase the scalability. So as Miguel showed a few slides back, we have achieved the almost linear scalability. So to handle twice this load, we need a little more than twice the hardware and so on. So this is the reference. So what are our conclusions? By separating different tasks and responsibilities, as well as the data stores, we delivered the desired horizontal scalability. This was the main aspect of it. The separation of transfers and participants not only increases the extensibility of the code, but it provides the data store partitioning without the extra effort. This is not easy to achieve, and by simply separating the concerns, transfers, and participants, we get this benefit almost for free. The code and integration example, the event-driven aspect, the CQRS and the event sourcing design effectively shifts the load to Kafka instead of a central database. This is really important because Kafka and the other data stores that we've been using in this POC, they are by nature horizontally scalable. So they were created to be distributed systems, and they have no issue growing in scale, which means that we have a lot of headroom to keep on scaling. We were concerned because we're distributing so much the transaction. We were concerned about the ability to perform a single transaction as fast as the current system. The POC is actually faster than the current design. We have shorter response times per transaction. So that part is really good news. And the final objective, but not the least important objective, was to make this central ledger design retrofittable, and we can confirm it is. So Importantly, we have produced a central ledger design that is faster, handles a lot more load, and is cheaper. This is the report out document structure. This document has been circulating now in the initial phase of the review, as we mentioned, and we'll shortly release it to the community. It has a few important sections that I'd like to call out. The first one is about the architectural principles and how we apply them in this design. The second one is about the performance and scalability results. There's a section about the learnings that expands all of the learnings that Miguel mentioned. There's another part that reflects how the central ledger and the PoC affects other and integrates other work streams like the settlements, bulk transfers, and what is required in terms of infrastructure change from the infrastructure perspective, because it's different. Finally, we have a section that explains what do we think is needed to transform this PoC exercise into a production-ready version of the central ledger. So including the non-happy path that we didn't build, obviously, and all of the design issues that we need to fix and that we need to continue working on to make it production ready. So as mentioned, we're receiving the initial feedback on this document from a limited set of reviewers. We'll be circulating this as well and vetoing it on the and voting it on the design authority. And we expect to share this document with the whole community for comment in a week's time. So immediate next steps are to review the report, as mentioned, and the design. We'll need to conclude some discussions around requirements that have an impact on the way we move forward. Sorry, I don't know what happens. I just lost my slide. So depending on those discussions, we'll need to make a final decision. That final decision will help us prioritize and make the production ready plan with the resources and the roadmap for the delivery of the production ready central ledger that is based on the designs that we achieved in this PoC. Can you still see my slides? Sorry.
We can, go ahead.
Okay, sorry.
Yes, we can.
Because I lost my view, so I'm just going blind. So how can you help? We'll need help reviewing the performance and scalability report. So as mentioned, it's going to be shared with the whole community in the next weeks. We need your contribution, looking at it, signaling out anything that we missed, and basically helping out with your contribution. Lastly, I'd like to thank the team for the dedication and commitment. This was an intense work done by a very small team. I'm really proud of what we achieved. So a very special thanks to the whole team. And that's it. Thank you.